Hello, welcome back class. This is video number 2 where we're continuing gas laws. I'm going to start right off and go over the learning objectives and talk about what we're going to learn this lesson. Okay, so when you are done watching this video, you should be comfortable with defining temperature. Understanding in science, typically we use 2 units for temperature, Celsius and Kelvin, and be comfortable converting between those units. Our last video we defined pressure, and hopefully you got comfortable converting between those units of pressure. And today we're going to start looking at what happens if pressure changes. How does that affect other variables, specifically volume? And we're going to learn our first gas law, Boyle's law. Okay, so your warm-up, just do it maybe in your notebook or wherever you're kind of jotting some things down so that you can do your homework. Obviously you won't turn this in, but it's good practice and it'll help you with the skills that you're acquiring in this lesson anyway. So hopefully you remember how to convert between Celsius and Kelvin and Celsius, okay? Going to Kelvin, remember you're always going to add because Kelvin cannot be negative. So if I'm going from 15 degrees Celsius, I'm going to Kelvin. What do I add? How many units apart are they? Hopefully you remember 273. So that would be 288 kelvins would equal 15 degrees Celsius. And it's not degrees Kelvin, it's just kelvins. What about Kelvin to Celsius? So it's just the opposite. So instead of adding, I am subtracting. So 273 kelvins to Celsius, I'm going to subtract 273 and get 0. So that is temperature, which is kind of where we're going to start in just a minute, but I told you we'd answer this question last video. Why do your ears pop when you go up in a plane or deep in a pool? So we ended last class talking about pressure, and I told you that pressure changes when you change elevation. So when I go down in a pool or up in a plane, am I changing elevation? Hopefully, yeah. You can say, clearly yes. And when you go up, the pressure gets higher or lower. The pressure gets lower. So what's going to happen here is because the pressure gets lower, okay, you have an eardrum, which is, think of a flexible, drum. Okay, that's what's interpreting noise right now. It's vibrating, and that's the noise you're hearing right now. So what happens is pressure can change that or change the shape of that eardrum and cause pain. And what happens when it pops is it's letting air in or letting air out of your ear canal, your inner ear canal, and it's equalizing that pressure. So when pressure increases on the, let's say the outside, if I go down in a pool, my eardrum is going to get pushed in, and that's going to feel uncomfortable. Okay, so the pressure on the outside is going to be greater, and it's going to push that eardrum in. That's going to feel uncomfortable. So what happens is there's a eustachian tube on the inside of your mouth. When you open it up, it can allow air to go into your inner ear and equalize that pressure. And the same thing happens when I go up in an elevator or go up in an airplane. The pressure goes down, so that eardrum gets pushed out because now the pressure on the inside of your ear is greater than the pressure on the outside. So that eustachian tubes allows for that equalizing of that air pressure. And sometimes when you have clogged sinuses and things like that, it's not that easy to do. And you can have a blocked eustachian tube, and it hurts. Okay, so that's pressure. Temperature. We're also going to be working with temperature today, so hopefully you know how to measure temperature with a thermometer. So what happens is that mercury in that thermometer expands. Remember, we've covered this before. It expands when it's heated. So that thermometer is just filled with alcohol, or used to be filled with mercury, but both of them expand when heated, and they travel up. We put a scale on the side, and that allows us to measure temperature. So what we're measuring, again, is that expansion or contraction of the liquid when you're measuring it in a thermometer like that. But what you're really measuring is the average kinetic energy of molecules, how fast those molecules are moving. If they're moving really fast, it's a high temperature. If they slow down, a lower temperature. And we're going to measure temperature with 2 units. Obviously, we're comfortable with Fahrenheit in the U.S., but Kelvin and Celsius are the temperatures that we use in science. Okay, and those are always 273 units apart. So make sure you're adding to get to Kelvin, subtracting to get to Celsius, and we're going to use that a lot this unit. Okay, so make sure if you don't know that, maybe write that down so that you're comfortable converting between units, going from Kelvin to Celsius or going from Celsius to Kelvin. Okay, all right. STP is another term you're going to hear a lot this unit. We've learned it before, but it's where a lot of experiments take place. So it's a specific temperature and a specific pressure where a lot of experiments, especially with gases, take place. So standard temperature is 273 kelvins, or 0 degrees Celsius. Standard pressure is 1 atmosphere. It equals a lot of other things that we've been converting between, but that's going to be the most common thing. If you remember 0 degrees Celsius or 273 Kelvin and 1 atmosphere, that is STP. So anytime I say STP, I'm actually giving you both a temperature and a pressure. Okay? All right. Now on to what we're really focused on today, and this is what your homework questions will be on, gas laws. So what we're going to do here is change variables and see how it affects other things. So we're going to maybe change pressure, change volume, and what happens is other variables are affected by that. So if I change the temperature of a gas, how does that affect the pressure of the gas or the volume of the gas? That's what we're looking at here. The first one we're going to look at was first discovered and written by a guy named Robert Boyle, and he studied a trapped gas and changed, saw how the volume was affected with the pressure. Okay, so what we have here is a J tube, and he had a big J tube in his apartment or his house, and he had a trapped gas here. So there's gas in the end of this J tube. Okay, so flying around, these are little particles. And what he did was he applied pressure here by adding more mercury. And when he pushed down here, what do you think happened to this? Make a prediction. So what do you think would happen to the gas in here? And you should think, well, it's going to get compressed, right? And that's what he did. He studied that. So how did volume relate to pressure? Okay, and that's what he wrote a gas law based on. So here I have so much mercury. Here's my volume of gas. If I keep adding mercury, I'm adding pressure, because that is a unit of pressure. And my volume of that gas changes. It goes down. So what I see here is a direct relationship, or excuse me, an inverse relationship. As pressure increased, volume decreased. So we call that an inverse relationship, and that is Boyle's law. And he wrote an actual mathematical formula to allow us to predict how much the volume would change when I change the pressure. And this can be useful. I mean, off the top of my head, it could be useful in making a hot air balloon or a weather balloon. Anything that's going to be exposed to differences in pressure, you need to prepare for that. So like if you have a flexible substance like a balloon, like a hot air balloon, you need to prepare for the expansion and contraction of that substance when it goes up and down when the pressure around it changes. Okay, so that's something that you can definitely use this in real life for. So we're going to look at a quick demonstration. I want you thinking while you're watching this demonstration, why is this happening? Why is this happening? Okay. All right. So hopefully this works. We'll kind of see here. Here we go. Great.
In a demonstration of Boyle's law, we'll place the balloon in a vacuum bell jar. We'll apply a vacuum, which basically pumps out the air in the bell jar.
All right, so what's happening here is the gases in this bell jar are being removed through the vacuum, okay? They're being removed. So the pressure in the bell jar is going down. So this is just like when you let a balloon go, a helium balloon, or a little kid lets it go, okay? And you see it float up into the atmosphere. Okay, what happens to that balloon? Do they just float around and there's all of these balloons floating around in space? No. Okay, eventually it pops. Why? Because as it goes up into the atmosphere, the pressure around it is less, so that balloon expands like we see here. Okay, so as that pressure goes down, the volume goes up, and that balloon expands. And then when he lets the air back in, you should see the pressure go down. So what happens with our balloons that you let go is they expand and expand and expand, but eventually pop. Okay, so if you ever find out walking, a popped balloon, that might have been some, little kid's lost balloon that he let go and it floated around maybe, miles, and then it popped, and that's what you see on the ground. But I don't think I've ever found or ever been looking for a popped balloon on the ground. But if you ever see one, okay? All right, so let's continue the video.
Pressure outside the balloon will be greater than the pressure inside. The balloon expands to try and equalize the pressure. Volume and pressure are inversely related to each other.
That balloon's getting
bigger and bigger. When we release the vacuum, the pressure increases and the volume decreases. As another demonstration of Boyle's law, we will put a marshmallow peep into our vacuum jar. The marshmallow contains air trapped in a mixture of gelatin and sugar. As we apply the vacuum, the pressure outside is lower than the pressure inside. Apply the vacuum, the pressure outside is lower than the pressure inside.
So because
the air in the peep will expand to try and equalize the pressure.
Because there's a lot of air in that peep, it expands as the pressure on the outside decreases, okay?
When we release the vacuum, the pressure increases and the volume decreases. As another illustration of Boyle's law, we will put some shaving cream into our vacuum jar. The shaving cream contains air trapped in a soap mixture. As we apply a vacuum, the pressure outside is lower than the pressure inside. The shaving cream will expand to try and equalize the pressure. As you decrease the pressure, the volume increases.
All right. So hopefully that makes sense, and that's kind of stuff that you can demonstrate. Experiment, you can demonstrate Boyle's law. So I would like you to just kind of, for practice here, write an explanation for why that happened. So put it into your own words. Why don't you pause the video and put it into your own words. Okay, so here's what I would write. I would say as the pressure decreased, volume increased of these expandable substances, and that is Boyle's law. Okay? And as the pressure increased, volume decreased, and that is also Boyle's law. Now you need a flexible substance here. You can't put like, a container, if I had this glass and put a lid on it, okay, I can't put that into the bell jar and expect it to expand because it's not flexible. But if it's a flexible substance, or like the peep or the shaving cream or the balloon, all of those are kind of filled with air and can change volume easily. They increase volume when pressure decreases and decrease volume when pressure increases. Okay, so what Boyle did is he collected data, numbers, and he saw this inverse relationship. Okay, and when you graph that, if you want a linear straight line, if you take P versus 1 over the volume, you get this nice linear line. Okay, rather than this kind of curve here. All right, so mathematically, that looks like this. Okay, this is Boyle's law. You can predict a new pressure or a new volume if you know 3 out of 4 variables. And this is at constant temperature and when the amount of the gas doesn't change. So those are 2 variables that don't change. So when I'm just changing pressure and volume, I can predict a new pressure and volume as long as I know 3 out of 4 variables. And that's just kind of basic algebra here, and that's what we're looking at. Okay, so Boyle's law is this. If I know the new pressure, I can predict the new volume. Or if I know the new volume, I can predict the new pressure. So that hot air balloon experiment. I know the pressure as I go up. So if I know the pressure as I rise into the atmosphere, I can predict that new volume. And we're going to do that in just a second with some homework questions. Okay, but this is Boyle's law. I would write this down somewhere so that you can use it on the 7 questions I'm going to assign for your homework. Okay. All right. So Boyle's law is pressure increases, volume decreases. Now, how do we solve these problems? So I'm going to follow these basic steps. As I'm reading through these problems, I like to underline or write down my variables that I know. And then that allows me to identify what I don't know and then rearrange the formula properly. Always ask yourself, is it logical? So if the pressure went up, the volume should have went down. Or if the volume went up, the pressure should have went down. Okay, always ask yourself, is it logical? Like this. Here's a quick question, and then I'm going to have you do a few. So a sample of chlorine gas occupies a volume of 946 milliliters. Okay, so there's my volume. Okay, at a pressure of 726 millimeters of mercury. There's my pressure. And you might even kind of put a P1 here and a V1 here. So these two go together. So I'm going to call them P1 and V1. What is the pressure? So I'm looking for my new pressure. I'm looking for my new pressure if the volume is reduced to 154 milliliters. That's my V2. So these are my variables that I know. This is the gas law that I'm going to use. Okay, so I'm going to be looking for this. So how do I rearrange this to solve for P2? Hopefully you're all comfortable. I divide by V2. So I'd take P1 times V1 divided by V2. Okay, cross multiplying, and that's going to get me P2. So I go through and I list the variables that I know. I rearrange the equation, and then I plug in and I solve. Now notice, these units, milliliters, cancel. And the unit for my answer is millimeters mercury. The unit here would be, let me move myself out of the way. The unit here would be millimeters mercury, because that's the unit of pressure that I started with. Okay, so I started with 3 sig figs, I ended with 3 sig figs. My unit was millimeters mercury, I ended with millimeters mercury. Please try to label everything. Okay, other things. If your units of volume don't cancel, you need to make sure they cancel. So sometimes you need to convert milliliters to liters or liters to milliliters. And remember, there's 1,000 milliliters in a liter. You'll probably see that on some homework questions. All right, let's do a problem on worksheet 8.1. So I think number 1 just said write a sentence explaining the demonstration you saw with the bell jar. Number 2 is our first problem. So I'm going to go through and underline kind of what I know. A balloon holds 1,279 liters. So what is that? That is a volume on the ground. The engineers are trying to figure out what the volume would be at 30,000 feet. Now this is a number, but is that a pressure or a volume? No. Where the pressure is only 0.6 atm. So there is my P2. Okay, and I'm looking for V2 because it says what is the volume. Now this one isn't as straightforward, but I want us to be able to read through this and understand what it's asking. So what size volume should be ordered? So I'm looking for V2, but what is my V1? Okay, well excuse me, what is my P1? Okay, so I know V1. I know P2. What is P1? Well, because it says on the ground, I can assume I'm at sea level. So what is the pressure at sea level? 1 atm. So anytime you see on the ground, your pressure is 1 atm. Or anytime you see STP, remember your pressure is 1 atm. Okay? All right. So my variables are V1 is 1279. P1 is 1 atmosphere because it says on the ground. I'm looking for V2, and I am given P2. So I'm rearranging this equation and solving for V2. Hopefully you're comfortable with P1 times V1 divided by P2 equals V2, plugging those numbers in and getting this new volume. Okay, and notice my pressure went down, my volume should have went up, and it did. Okay, but if I keep reading the question, it says they also need to allow for a 0.25% increase. Because you want to be safe, okay? If you're traveling up in a hot air balloon, you don't want to have, if I go up any higher, or if the pressure is any different than 0.6, it pops. I want to have some leeway. So I want a 25% extra fabric to be used to be safe. So how can I figure out 25% more of this? Well, if I want to figure out 25% more of this, I could multiply it by 0.25 and then add them together. Or I could just multiply this by 1.25. And that's going to be the volume of balloon that I'm looking for to be able to withstand this pressure change. Okay, so a little more challenging one in it, not as direct as the example, but hopefully makes sense as I walk you through it. I'm going to walk you through one more. All right, so number 5, 1 mole of any gas at STP is equal to 22.4 liters. If you have 3 moles of a gas at STP and the pressure changes to this, 922 millimeters of mercury, how much volume have you lost? So I'm looking for V2. Again, not as straightforward with what are my variables. So right here I see 22.4 liters, but that says of any gas. I have, 1 mole. I have 3 moles. So what would my volume be? It'd be 3 times that, because if I have 3 times that many moles, my volume is going to be 67.2. 22.4 times 3, because there's 3 moles instead of 1. Okay, now what is my pressure? Again, it says STP. My pressure is 1 atm. But notice this other pressure is in millimeters of mercury. I need them both to be the same. So I can either convert 1 atm to millimeters of mercury, or I can convert this millimeters of mercury to atms, which is what we did last video. So I chose to just convert 1 atm to 760 millimeters of mercury because that is on the front of my worksheet. So there's my P1. My P2 is 920. And I'm looking for my new volume. Okay, so I'm looking for my new volume. I'm rearranging, solving, and it looks like I get an answer of 55.5 liters. Okay, after my units cancel. Okay, so hopefully this makes sense. Oh, I forgot one thing. I'm sorry, I didn't read the question completely. How much volume have you lost? How much volume have you lost? So how much did I lose? If I started at 67.2 and my final volume is 55.5, again, my pressure went up. My volume should have went down. So how much have I lost? 11.7. Okay, so please be sure to read through the questions carefully if your answer doesn't line up before you ask, but I would always be willing to answer those questions. All right, so hopefully I see you in the meeting tomorrow, and we can kind of discuss what the next steps are. But our goals today were to understand Boyle's law, be able to convert between units of temperature, understand what STP means, and be more comfortable with defining and converting between units of pressure. So I do have a couple questions on this Ed puzzle to answer, and hopefully you're doing well there. And your homework, your assigned work, is worksheet 8.1, numbers 1 through 7. Okay, so hopefully this makes sense. If not, maybe watch it again or talk to me, email me, and we can get those questions answered. But that was Boyle's Law. Thanks.